All right, let's open up to page 347. We're going to take a look at some properties of logarithms today, and I hope that we can start to see a connection between the properties of logs and these properties of exponents that we dealt with in our last unit. So I know there's a connection, but like I said, I'm hoping we see it. I want us to just kind of review two of those exponent properties from last unit, because if you write them down, I hope that it's going to make that visual connection for us a little bit easier. So what if I told you that we had a to the m times a to the n? Okay, these are two exponential expressions being multiplied together. They have the same base. Can we use a property of exponents to help us simplify or condense those two expressions? Yeah? Add the exponents. All right, so notice how you kind of change two exponential expressions into one. You keep the same base, but it's the powers that change or they're being added together. So in this case, we'll add exponents. What if I had a to the m divided by a to the n? Can we use a property of exponents to help us simplify or condense that? Can I keep going? Yeah. How do we subtract them?
Exponents from the top minus the bottom.
Top minus the bottom. Okay, so in this case we subtract exponents. Okay, so it seems like when we're looking at the properties of exponents that addition and multiplication are linked. Okay, they have a connection together, and then subtraction and division are linked. Okay, they have a particular connection together. So we're going to see how these two properties from exponents are related to some of the properties for logarithms, because after all, logs are, can we finish the sentence? Logs are, say it again? Fun, okay. Okay, when you're finding the value of a log, you're finding the value of a, yeah, it's an exponent, it's a power. So if logs are powers, they should have kind of similar properties to exponents. So we're going to see how those are connected. So take a look at these two log expressions in this little box. I think we can figure these out in our heads. What power do we have to raise 3 to get 9? Say it again. 2. Okay. What power do we have to raise 3 to get 3? 1. Okay. And if we add those together, we get 3. This other log expression, what power do we have to raise 3 to get 27? 3. Okay. So notice how in both cases, this expression and this expression are equal. They are exactly the same. Okay, we get 3 for both of them. So that's telling us that somehow these two expressions on the left can be somehow changed into this single log expression on the right. Can you take a real hard look with these two log expressions and think about how you can manipulate them to turn it into this one? Do we see anything? We're adding them together. Okay, so that's something to make note of. If we're adding two logs together, yeah?
You multiply the 9 and the 3.
To get your 27. What was this 9 and 3 called in the log? the argument. Okay, so notice how these two logs have the same base of 3, which this other one did as well. And if you multiply the arguments together, you're going to get that new 27. So it seems like in this case, notice how addition and multiplication are linked. Okay, just like they are for these properties of exponents. So we're going to go ahead and jot that down in this first box. This is one of our first properties. In a generic case, if two logs have the same base and they're being added together, we can condense those two logs down to one single log that has the same base, and we're specifically going to multiply the arguments together. So I know it's a little different from the exponent property, because notice how for the exponents we were multiplying the bases, which means we add the powers. It's kind of the reverse or switched or inverse thought for logarithms. If you're adding the logarithms, you're going to multiply the arguments. Okay, kind of a switched concept, but they're still linked. They're still connected nonetheless. We can do the same thing for natural logs, okay, because the bases are the same. The base is e, like we saw yesterday, and we can multiply the arguments to get a times b. So what we're going to do is kind of write out this property in words. Sometimes it's a little bit easier for us to understand than just looking at kind of mathematical notation. So in this box, we'll write down if two logs of the same base are added, we can multiply the arguments to make one new log. Okay, I underlined the word one because you're going from 2 logs down to 1. Okay, you're condensing it, you're making it simpler, easier to work with. Do we see how this property of logs is kind of connected to the property of exponents, where we have that addition and multiplication being linked together? Okay, let's try the next one. Very similar. We're going to see how these 2 logs are related to this single log. So in our heads, can we think of what power we have to raise 3 to get 32? Two to the 5th. What power do we have to raise 2 to get 4? That'd be 2. And if we subtract 5 minus 2, that'll give us 3. What power do we have to raise 2 to get 8? 3. Okay, so again, notice how these results are equal. So these 2 log expressions should be equal, aka the same. So can you think about what we can do to these 2 logs to turn them into this one single log? Yeah? There we go. If you're subtracting the logs that have the same base, notice how you can divide the arguments. 32 divided by 4 would give you 8. So here's that connection again to the properties of exponents. Notice how subtraction and division are linked. Okay, there's a connection between the two. So in general terms, this is going to be our second property. If we're subtracting 2 logs with the same base, we can change them into one new single log by dividing the arguments. It doesn't matter if it's an log log or a natural log. Okay, it has the same property. All right, so we'll say in words, if 2 logs of the same base are subtracted, we can divide the arguments to make one new log. Are we doing okay so far? Should I take the silence as a yes? Maybe? Okay. I think for most of us, those first two are going to be pretty simple for us to remember because of the connection to those properties of exponents. These next three are going to be perhaps new to us, so we're going to have to focus our time on them a little bit more. I'm going to skip down to number 4, and then I'm going to come back to 3 and 5 and kind of use a calculator to help you visually see what's going on with these two properties. So if we take a look at 4, notice how in 4 the argument is being raised to a power. Can you think back to when we did properties of exponents? How did we simplify a power to a power? For instance, if I had x squared cubed, you multiply them. Okay, so if you have a power to a power, you can multiply the powers together. So what's going to be a little interesting here is this power of n, since it's a power, can be moved down as a multiplier, meaning a coefficient out front of the log. What are logs again? Logs are powers. So notice how we're taking this power of n times this log, which represents a power. So essentially, if you have a power to a power, you can multiply the powers together. This one's a little bit tougher usually for students to kind of grasp why we have this property. They don't really, or students in the past don't really have a problem remembering it. It's just kind of grasping the why behind it. But whenever you have a power to a power, we notice that how in exponents we multiplied those together. That's what we can do here. We can do the same thing if it's a natural log. We'll bring down that power and make it a multiplier, meaning a coefficient out front. So in words, we'll say if the argument is raised to a power, the power can be moved out front as a multiplier or coefficient, whatever wording you want to use. Okay, that one's a little different. For the next two, they're kind of related together. I'm going to go ahead and use a calculator as a visual for these. If you have one in front of you, you can kind of go along or maybe just want to pay attention to the board. What do you notice, first of all, that's kind of special about number 3? The bases are the same. Good. Okay, so notice how this base of b in the log is the same as the base b in the exponential function. Same thing's going on for the natural log. If we have a natural log, the base is e, and notice how that's the base of an exponential function. So in this example, the base of the log matches the base of the exponential. Let's see what happens if that's the case. So I'm just going to play around and make up some examples. I'm going to go to Math A, which is that log base option. We've seen it before. I'm just going to throw in some numbers for b and n. So for instance, if I want to make the base of the log 3, that means I'm going to need 3 to be a base in the argument spot. And I'm going to raise that 3 to some power. Maybe I'll just make it 4. Okay, so notice how this is an example of number 3 just with numbers in it. If I hit enter, I get 4. Let's try another one. What if I hit the common log button? What's my base? 10. Okay, so that means I'm going to have to need 10 in my argument, and maybe I'll raise it to the 15th power. Maybe I'll try a natural log. The base of a natural log is e, and maybe I'll make it the 600th power. Overflow. Maybe that was a little too big. We'll do 60. There. What do you notice? What do you mean by it? The exponent is the same. So what do you think's happening if this base of the log matches the base of the exponential? What are they doing to each other? They're canceling each other out because that's what's leaving us left over with this power. So if we have something that cancels each other out, that's what's called an inverse. You know how if you add 3 and subtract 3, you'll get 0, right? They cancel each other out. So if we have a log with a base b and an exponential with a base b, and those cancel, those must be inverses as well. They undo each other. So in this case, we're going to cancel those out, and it seemed like we're left with that power of n. The same thing happened for this exponential, or for this natural log example, where we were left with n as well. So we'll say in words, if the log base and exponential base match, they cancel to leave, in this example, we're left with the power. Okay? If the log base and the exponential base match, they cancel so that you're left with just the power. Can we perhaps think about what's going to happen for number 5? We have an exponential base of b and a log with a base of b. So what's going to happen with those? If you add 3 and subtract 3, they go away. If you have an exponential base b, a log base b, those are going to cancel. What are we going to be left with? Should we try a few on our calculator? We'll do 10 to the log of 6. We're left with 6. Let's do 3 to the log base 3 of 7. We get 7. We'll do e to the natural log of 9. We're left with 9. So if the exponential base matches the log base in this example, what are we left with? A, which represents the argument in this case. So if the log base and the exponential base match, they cancel to leave the argument. Okay, 3 and 5 are very similar, okay, because they have the same idea of canceling. It just depends on what you're left over with, and that depends on what the example kind of looked like. Notice how for number 3, you start with a log, and then your argument is an exponential. If that was the case, we're left with the power. However, in number 5, we started with an exponential, and your power was a log. In that case, we were left with the argument. So we have the same property, I guess, for 3 and 5. It just depends how it's set up is what's going to determine what you're left with, either the power or the argument based off the example. So keeping these 5 in mind, I would say 1, 2, and 4 are kind of the bigger ones that we're going to be using when we solve these logarithmic equations. But 3 and 5, since they're connected, are nice to know, because if things cancel out or go away, that's always a nice thing to kind of help us. So we'll keep those in mind, but 1, 2, and 4 are definitely the big ones that I want us to be comfortable with. So we're going to go ahead and practice essentially 1, 2, and 4 today and probably tomorrow by just looking at some examples to get comfortable with them, like how we can recognize which property to use and when to use it. So if we look at number 1 on the next page, some key things to look for, first of all, is to make sure that the bases are the same. That way we can use some of these properties of logs. And looking at number 1, they're both a base of 2. So we know we're good to go if we want to try to use a property. The second thing that I notice is that we're adding these 2 logs together. So perhaps we can use one of those properties we mentioned to help us condense these 2 logs down to 1 log. How can we do that? We have the same base and we're adding the logs. Go ahead, Elsie. Multiply the arguments. Okay, so I'm going to change 2 logs into 1 log. So I'm going to keep the log base 2, okay, all the way through. And my new argument should be the multiplication of the 2 arguments, which would be 6 and 8/3. So multiply those together and you get 16. All right, so maybe we'll leave it like that. We condensed it to a single logarithm. We just have to get familiar with what to look for, and then once we have that ability, using these properties might be a little bit easier for us. All right, if we pick apart number 2, I notice how the logs are the same base, which is good. I'm subtracting the 2 logs together, so that might be noteworthy. And then what's a little bit different from number 2 than from number 1 is that we have these numbers in front of the logs because we didn't really have those before. So maybe that would be something to be aware of. Can we use a property, or can we think about which ones, maybe we have to use more than one, which ones we could possibly use? Can we focus on these little numbers out front first, maybe? If we have a number in front of the log, a multiplier in front of the log, can we think about where that number was previously? Or where else we can write 1/3 or that 2? What do you think, Julia? Yeah. There we go. Okay, so this was, I believe, our 4th property. Okay, if you have a power on the argument, you can move it down as a multiplier. That's what we said when we wrote the property, but notice how we're kind of undoing that. We're working backwards. We're now taking a number in front of the log and moving it back to where it started. Okay, so that's definitely a property I like. Can we use another one? Remember, our goal is to get a single logarithm. I just want 1 log left. I have 2 logs with the same base, and they're being subtracted. Good, Erica? Yeah. All right, there's our new argument. So x to the 1/3 divided by y squared. So if you're subtracting the logs, we can divide the arguments. Again, just like these exponential properties, addition and multiplication are linked, and then division and subtraction are linked. So if we're subtracting logs, we can divide the arguments. Let's see if we can step it up a bit. Maybe we can do 3 logs. If that's a little overwhelming for you, maybe just for now ignore the last log and work in baby steps, perhaps. So if I just take a look at these 2 logs, okay, they're both natural logs, which means they have the same base, and I'm adding them together. So can I somehow change these 2 logs into 1 log by using a property? If we're adding the logs, what can we do to the arguments? Go, Grace? We can multiply them. Okay, so we got to take x plus 2 times x. So it's almost like distributing it in if we multiply them together. So it'll be x squared plus 2x. All right, so that's a property we can use on the first 2 logs. We have to remember, though, that we still have this other one on the end. I know we ignored it initially, but you can't just forget about it because it's still there. So it seems like we went from 3 logs down to 2. Our ultimate goal is to get down to 1 if we can. So can we use another property? I have 2 logs of the same base, and I'm subtracting them. What can we do to the arguments? Yeah? Divide them. All right, so this would be x squared plus 2x over x cubed. Right? Maybe we'll leave it like that. You could simplify. You can cancel out a set of x's because they all have that in common if you wanted to, but I say we'll leave it like that. All right, let's try number 4. 3 logs again. Let's be aware of some things to look for. Base 3, base 3, base 3, so they all have the same base. I have a mixture of adding and subtracting, and I also notice that there is a coefficient in front of that middle log. All right, so our ultimate goal is to get down to 1 log. Can we think of some properties that can help us get there? Is there something we can do with that 2 out front? Because that's what's a little different for this middle log compared to the other ones. Yeah?
Make it to a power of the argument.
Of the argument. Okay, so if I move this 2 as a power on the 3, that would be 3 squared. So my argument could be 9. All right, I like that. Can we use another property? Missy Headley.
You can multiply them and get 9x.
Okay, so if I look at these first 2 logs, they have the same base and they're being added. So I can multiply the arguments, get 9x. All right, that's going to help us go from 3 logs down to 2. We still got to go from 2 down to 1. What do you think, Caitlin? Yeah? Divide them. Okay, so we're going to keep the same log base 3, and we'll divide the arguments. So 9x over y. There we go. I like it. Are we starting to get into a groove a little bit? Looking or realizing what to look for helps a little bit. All right, so for number 5, they're all natural logs, so they're all the same base. We do have some division. Oops, I just gave it away. We have some subtraction. Darn it. I know. We have some subtraction. Bummer. I know. And then we have some numbers out front. All right, what can we do with those numbers out front? Move them up. All right, they're powers. Let's see. If we look at the first 2 logs, they are being subtracted. So I opened my big mouth before, and we can divide the arguments. What about the next one? We went from 3 down to 2. How can we go from 2 to 1? We have the same log being subtracted, so we can do what? Divide the arguments. Okay, so the question is, if I take this argument, which is already a fraction, and divide it by this argument of z, what's my final fraction going to look like? I'm gonna jot it down over here. We're taking x to the 1/2 over y squared, and we're dividing it by z. Instead of dividing by z, we could bring it up and multiply by 1 over z, the reciprocal. Okay, instead of dividing by something, you can multiply by the reciprocal. So that's technically not there anymore. So to multiply fractions, we're just going to go straight across. So it looks like up top I have x to the 1/2, and then my denominator is y squared z. A little tricky there. All right, so for those 5 examples, we were starting with multiple logarithms and trying to condense them down to 1 using the properties. Let's see if we can use the properties to perhaps go the other way. Let's see if we can start with 1 log and then expand it. Okay, turn it into 2 logs or 3 logs or 4 logs, whatever the case may be. So in this example, my base is 3, and my argument, if you want to put it in parentheses, is xy squared. So let's think about the properties maybe in a reverse sense. What's being done to the x and y squared within the argument? You're being multiplied. So if you're multiplying within the argument, how can you break up the log? We got to think about these properties that we just did, but in a reverse sense. If you're multiplying within a log, how can you expand those? Yeah? We're going to add them. Okay, so we're going to need a log base 3 of x, and then a log base 3 of y squared. Because the x and y squared are being multiplied, we're going to break them up into their individual logs, and since they're being multiplied, we're going to add those individual logs together. Okay, again, it's using the same properties we just did, but backwards, okay, in a different order. Is there another property we could possibly use here if we wanted to rewrite it differently? Toss the 2 in front. Informal, but yeah, toss the 2 in front. So that power of 2 we can move it down as a multiplier out front. I'd say that's probably as far as we can go, okay? So it's the reverse idea of what we did in the first few examples. Now we're going to start with 1 log and try to expand it a little bit further. Let's try 7, okay? I would suggest rewriting this as the natural log of x, y. What power can we put on the y if it's a square root? That's a half. Okay, so maybe that'll help us. What is being done within the argument? X and y are being multiplied. So that means I'm going to break up multiplication with addition. Okay, they're linked together. I'm going to need the natural log of x plus the natural log of y to the 1/2. Is there any other property we could possibly use? What, Elsie? To the front, yep. So 1/2 natural log of y. Looks good. All right, I think we'll be able to get one more in. Let's check this out. Natural log of AB divided by C squared. Can we perhaps list what's being done within the log? Yeah? We have 2 things. Okay, so we have something being multiplied and something being divided, so that means we should probably anticipate an addition and a subtraction. The question is, between those 2, which one is more overall present in the entire argument? The multiplication only applies to the top piece. Do you guys notice how the division encompasses the entire argument? So we're probably going to break that one up first. We can do natural log of AB minus natural log of C squared. Basically the top part minus the bottom part. All right, any other properties we can use? Can you keep going, Hadley? There we go. So since this argument is being multiplied on the inside, we can break that up with addition. Anything else we can do while we're on a roll? Yeah. Kick the 2 out front. All right, there's our expanded logarithm. Okay, so utilizing these properties, we can work both ways. We can go from multiple logs down to 1. We can go from 1 log to multiple ones. It just depends on what's appropriate for our solving process. Okay, because we're eventually going to get to solving these log equations. We'll save the other 2 for tomorrow as a good refresher.